Want to understand the changing world?
We break down all the big global shifts.
Follow us and never miss an update.
Hit that follow button right now.
Modern artificial intelligence models require massive computing power, and those server aisles generate an immense, compounding amount of heat. Terrestrial data centers are hitting a thermal ceiling. Active HVAC systems are working so hard to keep the silicon from melting that they now consume up to 50% of a facility's total power. To bypass the limits of air cooling, engineers are taking server racks and dropping them directly onto the ocean floor. This is the HiCloud facility, the world's first commercial underwater data center, built to support 24 megawatts of high-performance computing capacity. The capsules are deployed off the coast of Hainan Island and near the Lingang Special Area in Shanghai, placing them right on the doorstep of high-density populations. Relocating infrastructure underwater is a rigorous response to the laws of thermodynamics. The cooling capabilities of dry land have been exhausted. Submerging the hardware offers the only economically viable path to scaling the massive compute required for the next generation of AI. The efficiency of a data center is measured by its power usage effectiveness, or PUE. It is a ratio of the total amount of energy a facility draws compared to the energy actually delivered to the computing hardware. On land, average PUE is 1.5, with 40% of power dedicated to mechanical cooling. Enclosing servers in subsea capsules lets thermal load passively dissipate into the ocean. This compresses PUE below 1.15, reducing cooling to 10% of total energy use. Terrestrial facilities also evaporate millions of gallons of fresh water annually to manage heat. The subsea modules consume zero fresh water. Trading active mechanical chilling for passive thermal exchange in the ocean directly lowers operating costs, rewriting the economic equation for cloud providers. This setup creates an energy hub, physically linking subsea computing to co-located offshore wind turbines. The Shanghai HiCloud facility draws 95% of its electricity from nearby offshore wind, effectively operating off the main power grid to reduce transmission loss. Energy is only one half of the equation. Severe land scarcity in urban areas forces traditional data centers to be built far inland, physically distant from the users they serve. This distance creates latency. Edge computing applications, like real-time AI inference, require data processing to happen physically close to the user to eliminate microscopic delays in data transmission. This map shows how offshore deployments bypass the real estate problem. By sinking pods off the coast, computing nodes sit adjacent to high-density populations. Connected by short fiber optic cables, routing data directly to the coastline cuts transmission latency by 30 to 50%. Physical proximity to millions of users turns the seabed into highly efficient real estate, allowing it to outperform remote server farms for latency-sensitive tasks. Building underwater requires an immense initial capital expenditure, or CapEx, to ensure the hardware survives the environment. Deployed at 35 meters, the capsules endure constant hydrostatic pressure and aggressive saltwater corrosion, requiring specialized coatings like glass scales to maintain structural integrity. Maintenance is a severe bottleneck. A human technician cannot simply walk down the aisle to swap a failed server blade. Retrieving a pod requires specialized surface vessels and causes months of downtime. To survive, operators rely on a lights-out, fully autonomous operational model adopted from earlier industry prototypes. Before deployment, the interior oxygen is evacuated and replaced with inert nitrogen. Removing oxygen, along with eliminating human interference, drastically reduces component oxidation and mechanical failure rates. Inside the pod, AI-driven predictive maintenance systems monitor the hardware. If a node begins to degrade, the system automatically reroutes workloads to healthy servers to maintain the cluster's output. Trading physical accessibility for strict AI-managed autonomy is a mandatory compromise to make subsea deployment feasible. The operational efficiency of subsea pods introduces new environmental variables that engineers must mitigate. The active pumps and cooling systems generate acoustic pollution, creating the risk of disrupting marine mammal communication and navigation. This schematic shows how future pods must integrate acoustic dampening layers and non-toxic biodegradable materials to limit their interference with the local ecosystem. The infrastructure requires a calculated trade-off. Organizations absorb massive initial capital costs and severe maintenance logistics to achieve the OpEx savings in power, freshwater, and real estate demonstrated by the High Cloud project. As these facilities expand further offshore to meet global demand, they inevitably move into disputed maritime zones. Placing high-density computing hubs in these waters forces operators to confront new risks regarding physical security and data sovereignty. It establishes a hybrid network, pairing offshore renewable energy generation directly with high-density data storage. The intense power demands of artificial intelligence are pushing terrestrial electrical grids to their physical limits. To support the next generation of computing, the cloud is sinking to the ocean floor.